Thanks, everyone. We're presenting today the very first results of our research as part of the VMS Thematic Project. And I just want to start the talk by describing to you what melt inclusions are. The image in the left is showing you melt inclusions, trapped samples of magma from an eruption of Mount Etna that occurred just 10 weeks ago. And most melt inclusion studies have focused on very young rocks for many reasons, partly because these rocks have undergone far less change geologically. But we do find melt inclusions in ancient rocks, and the image below that is showing you melt inclusions from the 2.7 billion year old Bousquet volcanics in the DBL district. And this is the target of our research. This is the main focus, is looking at what these melt inclusions trapped in igneous minerals can tell us about the history of evolution of VMS deposits in the Archean. So I just want to acknowledge some project research partners and funding partners, Government of Canada, Glencore, and Agnico Eagle for providing samples and access to property for the purpose of mapping, as well as academic partners. And importantly, this project is allied with another VMS subproject, Project 3B, which involves researchers from Memorial University and the Colorado School of Mines. So just a brief overview. So the main focus of our research under this subproject is to provide insight into the evolution of magmas associated with Archean VMS deposits. Why is it that Archean VMS deposits differ so much from one deposit to another in terms of metal endowment? That's the key question. And the goal of this project, how we intend to answer that question, is to characterize the chemistry of melt inclusions hosted in minerals that are very inert, that preserve the history of that melt chemistry. And we're going to be not only characterizing the ore metal characteristics or the ore metal contents of those melt inclusions, but also volatiles. In addition to that, we're going to use mineral chemistry, and combining that with the melt inclusion data, the mineral chemistry is going to inform us about the conditions at the time of melt entrapment. So at what depth and temperature were those melts trapped in the Earth's crust? What type of specific crystallizing minerals were growing from that melt at the time of entrapment, as well as how oxidized those magmas are going to be. And all of those parameters together give us information about the fertility of VMS magmas. Specifically, can we identify using melt inclusion studies whether or not a specific magma in history was good at generating the right type of ingredients for VMS systems, or was it poor at doing that? And so a major focus of the application, not only within the Abitibi, but broadly on global VMS systems, is to be able to take this information and apply it on the district scale and on the regional scale to understand the differences between fertile volcanic units and barren volcanic units. And I really want to stress the novelty of this work. Despite hundreds of publications on melt inclusions as trapped samples of those original liquids in magmatic systems, there are no published data for melt inclusions in Archean age rocks. And so this is very novel, and it's a much needed study globally. So why study melt inclusions in zircon? Unlike many minerals that are compromised, as I said, preservation is the key in terms of the host phase. And so in a typical zircon, we typically have three categories of inclusion that are recognized. Silicate melt inclusions contain trapped samples of silicate liquid. From these, we can derive information about the metal content, the major and trace element content, and volatile content of the magma, including magmatic metal tenor. And also we can derive information about magmatic sources, identify processes like differentiation and contamination, and then we can reconcile that data with bulk rock data. These constraints also have a discriminatory value from the point of view of mineral exploration, and we can feed that information into mass balance exercises that are going to allow us to predict the size of volcanoplutonic complexes required to supply precious and base metals to hydrothermal systems. Sulfide melt inclusions are another interesting inclusion phase that typically shows up in zircon. And that's obviously providing direct evidence of sulfide saturation at some stage in the evolution of the volcanic rocks. And we learned earlier today that mineral inclusions are also very important because they constrain temperature FO2, as well as the host zircon, providing constraints on the geochronological and isotopic framework for the rocks themselves. And so the key point I want to make here is that we do need to combine, to get at some of the parameters we're interested in, combine the mineral chemistry with the melt chemistry. And the reason we have to do that is that there are some constraints that are very difficult to get at, such as oxygen fugacity, a critical parameter, for example, in controlling gold endowment. We can't get at that solely in highly oxidized systems using zircon chemistry. We know that there are mineral phases that are crystallizing at the same time that are going to be influencing the rare earth element chemistry of the zircon. And therefore, we can't extract from bulk rock geochemistry these parameters. And so we have to really go to the samples of liquid themselves. And so this is why melt inclusion data, as an example, allied with zircon data, can really constrain tightly these parameters that are so important. And I think an important point to raise here is that whether you're an advocate for active degassing as a metal source for VMS or passive leaching, the information that we can provide from melts can really inform both of those processes, because we're really interested in the metal chemistry of the fresh igneous liquids, and not these rocks that have been impacted so substantially in terms of their metal content by post-entrapment processes and mineralization. So I'm going to provide just a brief highlight of an upcoming paper that's coming from our group at St. Mary's University. This was work done by Dan Marr, who was an MSc student funded under the TGI-5 initiative. Dan recognized silicate melt inclusions in quartz phenocrysts in the Bousquet Formation volcanics within the DBL camp. These inclusions demonstrated up to several orders of magnitude higher gold, arsenic, antimony, and bismuth than normal crustal abundances, and many orders of magnitude higher than the host volcanic rocks, as can be seen in this diagram here. And furthermore, Dan used laser Raman mapping to show that the melt inclusions in the Bousquet volcanics contain immiscible carbonic liquid phases. These were trapped long before emplacement, indicating that the melts were already saturated in volatiles in the deep crust at the level of TGG magma generation. And thus, at the stage of emplacement, some metals had already been lost through deeper devolatilization. So clearly, this work has important implications for very gold-rich VMS systems like Laurent-Penna, but also probably more broadly for orogenic gold in the Archean. And the fact that there's overlap between melt inclusion metal contents and VMS ores in terms of composition stresses the predictive power of this study. So Priyal's going to take over now and explain where we are in the Zircon melt inclusion VMS project at its very early stages.
Okay, thanks, Jake. So we have chosen 3 VMS districts for our main study areas: the Kidd Creek Camp, Durham, Bousquet, Laurent Camp, and the Noranda district. These have been chosen because of their differences in metal endowment, specifically their gold to base metal ratios and copper, zinc, and lead ratios. We'll also be studying some lithologies from volcanic assemblages that lie within and outside of our main VMS camps, so that we can compare barren volcanic assemblages to metal fertile assemblages. And within these volcanic assemblages, we are looking at lithologies throughout the stratigraphy so that we can understand stratigraphic changes in the melt chemistry across the mineralized volcanic horizons. So for example, in the Kidd Creek district, we have lithologies from the footwall, the ore body host, as well as the hanging wall, and these represent the pre, syn, and post ore volcanic units. Next slide, please. So just to put our sample suite into context, we have quite a large number of samples from our 3 main VMS camps, including different lithologies from these camps. And we have a couple of other samples from areas surrounding these three main study areas. Next slide, please. So we have managed to collect a number of samples from archived hand and roll core samples, as well as zircon separates. We need a large number of zircons for the study because the inclusions in the zircon are generally rare, and some zircons are of poor quality, and we generally need a good zircon host to study these melt inclusions. So half of the population of zircons are being mounted as is, and the other half are being annealed at 900 degrees Celsius. This is so that we can obtain bulk chemistry for the silicate melt inclusions from homogenized inclusions. So the methodologies that I'm undertaking are thin section petrography to identify lithologies that contain zircon and establish the timing of zircon growth relative to other rock forming minerals. Melt inclusion petrography to screen zircons that have good quality melt inclusions. This will be based on origin, size, depth, shape, and preservation, as well as the degree of recrystallization of the melt inclusions. And we're also taking a look at presence of accidentally trapped phases. Scanning electron microscopy is used to look at the bulk inclusion composition of exposed melt inclusions, and electron microprobe is going to be used to obtain some major element chemistry and mineral chemistry for allied thermobarometry. The main technique that we'll be using is LAICPMS to obtain or to quantify major and trace element composition for both the melt inclusions as well as the host zircon. And we'll also be doing some Raman spectroscopy to assess the volatiles of the mineral inclusions. Next slide, please. So just to give you a brief overview of some of the results I've observed so far. I've seen quite a number of silicate melt inclusions hosted in the zircon. Generally, most of these melt inclusions are well preserved as they show a glossy texture, but some of them have been recrystallized. There's also the presence of various mineral inclusions, mainly apatite. We see some biotite and quartz, and a few other mineral inclusions. As Jake mentioned earlier, these are important so we can use some of these inclusions to, or some of these minerals to constrain the oxygen fugacity, for example, epidotes and oxides. The biotite can be used to constrain volatile saturation, and we can use the rutile to constrain titanium activity, which can be used for zircon thermobarometry. And lastly, we also see some sulfide inclusions trapped in the zircon. These are multiphase sulfide inclusions, specifically copper-rich, and they are coeval with the silicate melt inclusions. And these show evidence of sulfide saturation within the system. Next slide, please. So I've plotted some of the bulk composition of the silicate melts on a test diagram. As you can see, they show a wide spread of data ranging from alkaline to subalkaline. And the bulk composition of the silicate melt inclusions vary within single lithologies. So this confirms that they record melt evolution scales that are not represented by the host lithology. Next slide, please. So just a timeline for the project. It initially began in winter 2020, where we started to gain access to samples, labs, and personnel. We screened about over 6,000 zircons from the Craton scale archive to identify our study areas. Unfortunately, we had a 9-month delay due to COVID, but we managed to catch up somehow, and we are here in 2021, where we have selected zircons from our study areas. We have been able to get them mounted and polished. I've been able to do some preliminary petrography and method development, as well as my PhD coursework. And then moving on to spring 2021 to summer 2021, we'll be prioritizing samples from the Kid Creek and Daya and Buscay camps. We'll be doing some petrography, electron microscopy, and Raman spectroscopy analysis, all to be done at SMU. And I'll be preparing for my qualifying exam and proposal defense. Moving on to summer 2021 and spring 2022, we'll be focusing on LAIC PMS, which will be done at Memorial University and University of Geneva to look at the zircon and other accessory mineral chemistry, as well as major and trace element chemistry of the sulfide and melt inclusions. I'll be doing some presentations at GAC and SEG and some methodology workshop to Glencore and Agnico Eagle. And then by spring 2022, we hope to draft our first manuscript for the Kidd Creek deposit. And that's it from us. Thank you.